Our last speaker is Stephen Balbus, talking about angular momentum transport and turbulent disks and stars. Oh, you switched it in your...
Oh, well, I just forgot what my title was. Been known to happen.
Let's see. Put that somewhere.
Okay.
Should be on. And you won't be able to tell it's on.
Okay.
Wonderful.
So today I'd like to talk about where we stand with our understanding of angular momentum transport in astrophysical disks and stars, and particularly in the case of stars, the related convection or convective transport that goes with that. Already? It gets much worse. That's transport. That's large-scale transport. All right, if you can ask, make them good questions. Oh, that's a kind of an inside ENS joke. That's the motto, or that's the logo for the physics department at the Ecole Normale. So that's a little bit more obscure. That's a good question.
The turtle on these slides, that was an inside joke.
All right, I'm going to move on if we can. So accretion disks, of course, have become literally a modern icon for astrophysics, in particular high-energy astrophysics. The notion of an accretion disk, which I guess in its modern guise arose in the 1960s, has become the iconic emblem of X-ray astronomy and the production of high-energy gamma rays. So it's important to sort of understand the basic properties of disks, which for many years remained rather mysterious. The basic problem was that for an accretion disk to actually accrete, that involved the loss of angular momentum from fluid elements. Angular momentum, of course, fluid elements tend to conserve their angular momentum. So the question was, how did this come about? What provided the necessary torques? Well, accretion disks are made of gas. A gas has an ordinary viscosity. But the kinds of systems we're dealing with here are very, very small mean free path, highly collisional systems. And it's easy to show that, as is often the case in these kinds of rotating systems, you don't have to go to an accretion disk. The classic example that we learn about in hydrodynamical classes is a cup of tea. And if you try and exert torques with ordinary viscosity, if you stir your tea and let it slow down, you find that the slowdown time in the case of a cup of tea, the accretion time in the case of an accretion disk, is off by orders and orders of magnitude. So something else is going on. In the case of a cup of tea, of course, it's secondary Ekman circulations, which are involved with the angular momentum transport. In an accretion disk, there are a variety of very good reasons to presume that what is involved here is ordinary turbulence, enhanced transport that arises from turbulence. And in particular, the correlations between radial velocity fluctuations and azimuthal velocity fluctuations are particularly important. These can be, if there's good phase coherence, the dimensional velocity squared that emerges from this correlation coefficient can be orders of magnitude larger than the ordinary diffusive viscosity. So the question was, how does that come about? Let's ignore that for the moment. That's not a trivial point. That took several decades to get straightened out, exactly why there's such a powerful correlation. But let's see what its consequences would be. So if I write down the angular momentum flux by doing a rather standard Reynolds expansion. That is to say, I assume that the velocity v phi is the Keplerian velocity plus a fluctuation, and the radial velocity is basically a fluctuation plus a very small drift velocity. The drift velocity I can't ignore because that is why the object accretes. So we want to keep track of that. So if I expand the angular momentum flux, I get one piece proportional to the correlation delta VR, delta V phi, plus another contribution to the transport, rho r cubed omega. Omega here is the angular velocity. Let me just say a word about notation before it gets too confusing. I'm going to try to use capital R for cylindrical radius. Phi is the azimuth. And I think in the accretion disks, I don't talk very much about Z. Omega is I will use for Keplerian angular velocity. Omega squared is gm over capital R cubed, where m is the central mass. So this angular momentum flux, if it is present in a steady disk, must be constant. And so this immediately gives us an expression for what the inward drift velocity is. And this is sort of a nice example already of kind of a fluctuation-dissipation relation. There's nothing particularly diffusive about the fluctuations themselves, delta VR, delta V phi. You can have them present if you have just ordinary adiabatic waves traveling around in the disk. But if they're correlated, if there's a strong correlation, there is associated with it this inward dissipated drift velocity, which is, of course, the mass accretion rate. This is what we're after. And so this is a simple and direct example of that kind of a relationship.
Can I ask a question here?
Sure.
That seems very phenomenological so far. What am I missing? It seems like it's a made-up equation.
As far as I know, angular momentum
Well, I mean, you haven't written down any conservation of toroidal angular momentum equation or anything. You just heuristically.
I'm going a little fast. I could write down the Euler equations of motion, and then I could show you how if you write them in conservation form, they have an angular momentum flux. I've jumped a little bit ahead. That is the angular momentum flux.
Is this a plasma or is it a fluid?
I suspect it's true for both. I don't know, I mean, the plasma physicists here can correct me, but R VR V phi is an angular momentum
Well,
flux.
that's only a portion of the.
No?
There's a viscous stress tensor. There's gyral viscosity as well as collision.
No, so this is, all right, in some sense, this is a fully collisional system. Now, the viscosity in principle would be present there, but in our particular example, it's totally negligible. Which is why we're resorting to a turbulent approach to this.
You told us it was a long mean free path system, so why?
I'm sorry?
You told us it was a long mean free
No,
path.
small. If I said that, I
Okay,
misspoke. I'm
right,
sorry.
I understood that.
It's a small. It's a fully collisional system.
Okay, thank you.
Okay.
There's also magnetic stress, but
Well, we're going to get to the magnetic field later. In fact,
right.
and that's certainly an important.
That's your punchline. But this is an exact conservation law for a fluid equation. Fluid system.
Okay. So all that I've done here, as I said, there's nothing. This is about as close as to first principles as we're going to get. So. Now, if I look at what happens to the energy flux by going through the same type of argument by expanding the radial velocity as a fluctuation, delta VR plus a drift, then I find there are two terms that are present. Interestingly enough, the only turbulent combinations that come into the argument are the correlation tensor delta VR, delta V phi, and the radial drift. So in other words, we saw those already in the angular momentum flux. When we go to the energy flux here, there isn't anything new that pops out. So this is actually quite convenient because we can relate from our previous fluctuation dissipation relation, we can relate what the drift velocity is to the correlated fluctuation delta VR, delta V phi. So if I go ahead and I put in that substitution, I find that the total energy flux is minus 3/2 rho r v squared phi. That v squared phi is the 0th order rotation velocity of the disk times the drift velocity. Now the angular momentum flux had to be conserved. I can't get rid of angular momentum, but there's nothing sacred about the energy. And in fact, what I can't have in this example, if I have a constant mass accretion rate, I in fact cannot conserve my energy. Energy must be dissipated by this transport. If I take my expression for the energy flux and I impose the fact that 2 pi rho r times v drift, essentially that's the accretion rate, I should be a little more careful and do a height integration. So ignore, in this simple approach, the z variance. So if I actually take the divergence of that flux, I find that I can do so explicitly. And I find, in fact, that there is an energy dissipation per unit volume given by the expression that you see on the board there. 3/4 pi gm m dot. M dot is the constant accretion rate over r cubed. And this is the classical Lynden-Bell and Pringle result derived by different methods. Oh gosh, almost 40 years ago now, just on the other side of the street here, for why an accretion disk is visible. This is, of course, the source of the accretion disk's luminous energy. And those of you who have been through the topic before will wonder why this is not an 8 pi instead of a 4 pi. And the answer is that there's two sides of the disk, and each side emits 3/8 pi, for a total of 3/4. Well, let's talk about lies, damn lies, and turbulence phenomenology. This is all well and good, except that it's wrong. The problem is that delta VR and delta V phi lack phase coherence in the Keplerian disk. And I think we understand this. I think Isaac Newton would have understood this perfectly. This is because if I disturb delta VR and delta V phi, they do epicycles. And the fact that there may be pressure present doesn't change anything. I'm still out of phase, and this correlation, this time average delta VR, delta V phi, is essentially 0, and it is very difficult, if not impossible, to achieve this kind of turbulent transport, to have any sort of significant level of shear turbulence. You can arrange other forms of turbulence in the disk. I'm not saying that it's possible to have any instabilities or any type of turbulent process present, but this kind of shear turbulence that depends upon correlated fluctuations in delta VR and delta V phi is, as far as we know, impossible to achieve just with ordinary hydrodynamical processes. And in fact, an experiment by Han-Tao Ji at the Princeton Plasma Labs a few years ago, where they had basically they were setting up a magnetized fluid Couette experiment, which they started out with doing an ordinary hydrodynamical Couette flow experiment. They got to Reynolds numbers of order several million and found no trace of shear instabilities, which, by the way, was quite a surprise to many members of the community. If you take out Landau and Lifshitz, they will tell you it's not even an issue that at sufficiently high Reynolds numbers, any differential rotation profile is unstable. That is just the way it is. And I'm not sure where that insight comes from, but if it is true, you need to have Reynolds numbers well in excess of several million before this comes about.
Very Lifshitz rather than that.
The only possible explanation. And as Greg said when he stole my punchline, All of this changes, of course, when a magnetic field is added. And that's because even a very weak magnetic field renders differential rotation, if it's decreasing outward, renders it unstable to what is now known as the magnetorotational instability, or MRI. And the explanation for this is probably pretty familiar to most. Let me quickly run through it. If I have an inner fluid element which is rotating faster than an outer fluid element, omega 1 is the inner one, omega 2 is the outer one, the magnetic forces are proportional to the displacement, so they act very much like masses on a spring. In this case, there is a torque exerted backwards on the lower fluid element and a torque which is exerted forward on the upper fluid element. So the lower fluid element loses angular momentum, falls in, but acquires angular velocity in the process. So we have to make a careful distinction between angular momentum and angular velocity. The upper fluid element, on the other hand, acquires angular momentum. It moves farther out and it slows down. But now I have an even greater shear between the two, and the process runs away. You can see just from the basic setup, if I flick this back and forth, that I'm going to get precisely, even in this cartoon, you can see I'm going to get precisely the sort of delta VR, delta V phi correlations that I need to make this work, and they're in the linear theory already. More formally, if you go through the equations, you can show that the instability criterion is that kVA squared, the alphane frequency squared, plus d omega squared d log r. The shear must be bigger than 0 for instability, so at long wave numbers, and this ultimately decides whether in a particular disk, depending on the strength of the magnetic field, whether you're stable or not, your wavelengths have to fit inside the disk. But if kVA squared can be made small so that it doesn't interfere with d omega squared d log r, of course for a Keplerian profile, the angular velocity derivative is negative and we are unstable. By way of contrast, the Rayleigh criterion involves the angular momentum gradient, which is always positive for a Keplerian profile. The angular velocity gradient is negative. Bottom result is that the MRI introduces powerful correlations between delta VR and delta V phi, as well as correlations between the alphane velocity, the radial alphane velocity, and azimuthal alphane velocity. And now, in our stress tensor, we need to go back and include those in our analysis. But the upshot is that the argument that I just went through before, the one that was based purely on hydrodynamical considerations, conservation of angular momentum, energy dissipation, that goes through precisely. There's no changes, except that whenever I had a delta VR, delta V phi, I need to amend it to include the alphane contribution. So that's why it's worth going through the hydrodynamical argument, even though it's formally incorrect. You get the right answer anyway. The stress tensor, TR phi, and in fact, if I were more careful, I would have included the density there. It should be a density-weighted stress tensor. That's a fundamental object for transport theory in disks. Among the several roles that it plays, one of them is to extract energy with, or I should say from, the free energy source of the differential rotation. Minus TR phi times d omega d log r, the stress by so-called stress by strain relation. This is the rate at which energy is exchanged with differential rotation. Interesting and important point. There's nothing particularly dissipative about the presence necessarily of TR phi and d omega d log r. This is the rate at which energy goes from the differential rotation into the fluctuations. At that point, if I'm talking about an adiabatic wave, the wave can propagate through the disk, perhaps even transport angular momentum, without any dissipation. At some point, you need to dissipate the wave to deposit its angular momentum. But that term can be present. It simply represents an exchange between the fluctuations and the differential rotation. What makes an accretion disk, an MHD turbulent accretion disk special is that in the example that I discussed, that energy cascades not just from the differential rotation to the fluctuations, but it's dissipated locally in the disk. It doesn't go anywhere. So turbulence dissipates locally for the waves. The possibilities are far more open. Now here's some actual data, which is not widely known, but I find it rather impressive. So this is an X-ray source, a very famous X-ray source, Cygnus X1. And what we're looking at here is is a normalized flux. So it's the X-ray flux measured at the Earth. And this is kind of a probability distribution function. The absolute numbers don't matter here, but this is where the luminosity is most of the time. And then it trails off here, and it trails off down here. And you'll notice it's not a random phase Gaussian. It's a log normal fit. Now, is that something that we can understand in terms of a process, if not the MRI, a process like the MRI? The key point here is that it's log normal, and it's log normal to a very high level of accuracy. One sees precisely the same things in numerical simulations. We can't do radiation processes yet in simulations of accretion disks, so we use some kind of a proxy. So this is work by Chris Reynolds, and what Chris did was essentially, the essence of what he did was to look at that drift velocity term, or if you will, the delta VR, delta V phi correlation. And he measured what percentage of the time did it have this value, what percentage of the time did it have that value, did similar statistics, and in fact, you can't quite see it. There's a very faint dotted line, but the Gaussian fit is terrible. The log normal fit is rather good. Why would the MRI give you this sort of a log normal distribution? Well, the answer is, the quick sketch here is that the MRI exhibits linear local exponential growth that's abruptly terminated when a fluid element runs into another fluid element going out, hits a fluid element going in, they come together, they mix, the exponential growth is terminated. Now, the particular lifetime of this linear growth phase is very likely to be a random Gaussian process. It just depends how long it goes on before it bumps into another fluid element. The local amplitudes of the fields grow like an exponential, e to the AT, at which point they're thermalized and radiated, and this is responsible for the observed luminosity. Now, if the time is a Gaussian random variable, then the exponential e to the AT is a log normal random variable. So this is, I think, an interesting, at least it's consistent with the notion that's what's producing the turbulence here, goes through exponential phases that are abruptly terminated when the fluid elements meet and mix. And I would be remiss if I didn't at least show you what this looked like. So here are some old classic simulations by John Hawley of accretion tori. On the view on the left, we have a meridional slice. The view on the right is the equatorial plane. We are looking at the density here, and I think the initial configuration was field loops within the disk, within the torus, I should say.
So it's a tokamak.
It's like, yeah, it's a low density tokamak.
Exactly.
So the fluctuations are significant not just in like a thin layer on the surface,
No, not at all.
throughout the entire object.
Exactly. And in fact, it's where exactly the energy is dissipated with height turns out to be a question that we don't know the answer to at this point in any kind of satisfactory way. It's not an answer we would like to know, because it would it would enable us to be able to predict from first principles what the emission spectrum of the disk will look like. Yeah.
I've heard people say but the beta must be way too high inside the accretion disk for any of this magnetic stuff to be important. Anonymous astronomer. I mean, that's just not the case. Good to know.
Beta can be high, beta can be low. Yeah.
Can't be too low.
No, it can't be too low because
High
the
is
disk is
good.
there.
High is good.
Yeah, and I think, I mean, it depends, right? If the beta is so enormously high that the wavelengths have to be so tiny to get any appreciable tension that they're dissipated, then that wouldn't be good. But betas of 1,000 or 10,000, 100,000, those are fine. Those are fine. This is a weak field instability.
Sorry, another question. The argument you made for the log normal distribution of the magnetic field. So from that point of view, you would say that the same argument will apply to the distribution in the saturated state of
That's right.
anything in a turbulence that grows via an instability.
That's right. If in fact,
You stole my question.
I am sorry. but there's evidence against that, at least in some cases, I think.
no, I would be. You are right. The argument that I gave was in fact a little bit glib, because the nonlinear phase of an instability might not look anything like the linear phase. For the MRI, I would say you're on a little bit stronger ground because you can actually see these things in the simulations. You're constantly playing off of the background field, getting fluid elements to stretch and to grow exponentially.
You're doing this in any instability-driven.
Well, and also
Well,
what may help here is that the MRI linear eigenmode actually is a nonlinear solution.
Well, under
Unless it
under certain conditions of symmetry, yes. Not that's not always the case. Yeah, but there are solutions. Yeah, it's basically it's the nonlinear Alfvén wave solution. Yeah, that's right. So I would say in the MRI there's more memory of the linear state than there tends to be generically. But the comment is a fair one. I wouldn't go to the mat on this. Yes.
When these simulations are done, do they start with a particular equilibrium that they run from, and what role does the magnetic field play in that?
Yeah, not necessarily. The betas that people are using are typically so high. So the equilibrium, I see what you're saying. The equilibrium here is not necessarily an MHD equilibrium. You can use the magnetic field itself and the out of equilibrium initial condition to see the perturbations.
So it's seeking a new equilibrium by the MRI developing?
Right, but the equilibrium that it's seeking doesn't look anything like the equilibrium that it started with. The equilibrium it's seeking is singular. It wants all the mass down at the center of the potential and all the angular momentum out at infinity. The accretion disk is just what the gas has to go through in between to get to that state.
The initial state is in gravitational equilibrium.
Yeah, rotational
And the
gravity.
magnetic field is weak. These are typically betas 400 in these cases. So the magnetic field pressure, if it's out of equilibrium, it's only very slightly out.
No, that's what I was trying to say.
What happens to the instability growth rate as the magnetic field goes to zero?
Well, that's a nice question. It's one of the nice features of the magnetorotational instability. The actual growth rate, I haven't shown, the actual growth rate, the maximum growth rate, is independent of the strength of the magnetic field. It's an MHD instability whose criterion for instability is independent of the magnetic field and whose maximum growth rate is independent of the strength of the magnetic field. So it doesn't change.
The wavelength goes to zero.
Yes.
The wavelength of maximum growth gets smaller and smaller, and ultimately it becomes dissipated. In fact, that was accretion disk theory sort of began in the 60s, and it took a long time to find this. And it was because of the fact that magnetic fields were considered, certainly in the astrophysical community, as incredibly messy things. People who worked on magnetic fields were objects of contempt. They gave boring, incomprehensible talks. And everybody knows.
Those don't always go together.
This proud tradition survives.
And everybody knows that basically the universe is the way it is because of hydrodynamics. In magnetic fields, they're a complication, but that's not really a fundamental process. So what saved the day here for the MRI and this was sort of the thin edge of the wedge, was that you could actually retain these sort of salient properties of the MRI in the limit when B goes to 0.
I'm getting
Yes.
confused. In the limit when B goes to 0, you don't recover this instability though from the fluid equation, the standard hydrodynamic equation.
It depends what direction you're coming from. So it's one of these singular limits. In other words, if you start off purely hydrodynamically with B absolutely equal to 0, then you're right. You get the Rayleigh criteria. But if you put a B in from the very beginning, you do the analysis, and then at the end of the calculation, you let B go to 0, and then the growth rate and the stability criterion remain intact as B goes to 0.
So suppose you just put your magnetic field into the equilibrium. Suppose you actually had a true equilibrium. Would you find there was no MRI in that case?
Well, probably no. I mean, the MRI would be present provided that the field was not so large that all the wavelengths that could sit inside the disk were stabilized by alphanic tension. That's right. The equilibrium state is not a real concern here in general.
Well, I'm wondering how much of what you see is because you don't have the magnetic field at equilibrium, or said another way, there really isn't a true equilibrium here. You have to start it from something that's not a real equilibrium, and it's trying to...
Who cares about how you started? The real systems don't have...
I was going to say, right, nature isn't sitting here, during the calculation and, waiting for an equilibrium to achieve before she puts in her perturbations. This is the way the real things work. But even taking your comment as a formal point, I don't think that is true. To give you a trivial example, if you put in a vertical magnetic field, you could easily have an equilibrium, because the vertical magnetic field doesn't actually do anything.
Right.
And so, but even if you had, my guess is that if you put in a weak magnetic field and sort of carefully arranged an equilibrium, the MRI would be present anyway. The terms that are destabilizing are not the out of equilibrium terms. Yes?
Just in the density thing you showed there, it looked like the high density did something like a flare. Or at least it flared out towards away from the center point. And what's a simple explanation for that? And can that explain some of these things that they think they see?
Well, the flare disk, that's probably the flaring that they see in astrophysics is probably a radiative process of the outer edge. This is simply sort of a dynamical result. You get a constant opening angle when you actually put in finite pressure effects. Because it's not something which is directly related to the disk flaring that people worry a lot about. Let me just make one other important point before I move on. This is one of my favorite slides. On the left, you see what my country used to call a device back in the 1960s when I was growing up. It was China test nuclear device. This is a drop of water upside down, which is just plunked into just a container. And what's remarkable here is that the Reynolds number here is 10 to the 11th, and the Reynolds number here is 10 to the 4th. Yet qualitatively, these two things look very, very similar. Of course, you see, as you would expect, far less fine-scale structure in the drop of water than you do in the atomic bomb, but the gross global features are very similar. So the point is, large Reynolds number flow looks more or less like other large Reynolds number flow, even though the Reynolds number may be a factor of 10 to the 7 different. Unfortunately, this does not appear to be the case for MHD turbulence. That is to say, it seems to matter what the physics of the dissipative scale is. You can get gross differences in the saturated state of the MHD turbulence induced by the MRI, depending upon whether, in particular, you have two dissipation coefficients that are important in MHD, of course, the viscosity and the resistivity. Now, normally the resistivity is the more important of those. the ratio nu to eta, magnetic Prandtl number, is small in an accretion disk. But it is not always the case. There are, how shall I say, in the inner portions of X-ray sources, for example, the magnetic Prandtl number can become very large. It's very small in the outer portions of the disk. And the degree of coherence, the level of saturation, the level of the stress tensor, all can depend upon precisely what that magnetic Prandtl number is, even though it's something which is going on at very small scales. Now, maybe that won't surprise this audience, but it was a big surprise in the astrophysical community. And in fact, many of the people who are involved with that are here in the room today. John Papaloizu, Alex Shekuchian were involved with elucidating this very important property that, in fact, MHD turbulence depends on what the small scales are doing. And this is still very much sort of an ongoing area of research to understand how this plays out. Let me skip over, since I'm running a little bit short on time, to talk about stars. Talk about angular momentum transport in stars, which is a very different problem. The canonical problem is the sun and the solar convective zone, and to understand why, as I say here, why convective stars spontaneously develop differential rotation. I have a star which is in uniform rotation, and there's a convective zone present. The convective zone develops unmistakable, very striking differential rotation. Now, a convective zone is characterized by a good correlation between velocity and temperature fluctuations. T here is now, this is not a stress tensor, that's a temperature fluctuation. And these are designed by nature to transport heat, not angular momentum. Heat goes out very efficiently, while angular momentum, at least in the early stages, tends to go in. Ultimately, the angular momentum transport is complicated. But here's why, in the first place, a uniformly rotating convective system tends to develop differential rotation. At least this is the way that I understand it. So imagine I have a convective system, two fluid elements, L1 and L2. Omega 1 is equal to omega 2 in the initial state of uniform rotation, but the angular momentum, L1, is less than L2. Now, the convection moves the fluid elements together where they come together and they mix. Each of them tends to preserve its angular momentum in the process. So when the elements meet, L1 is less than L2. But they're meeting at the same radius, of course. So when that happens, if L1 is less than L2, omega 1 must be less than omega 2. And in order to get dissipation of the mixing energy, I'm fast on the outside and slow on the inside now when I actually mix the fluid elements. And so it tends to push the angular momentum downward. The core of the star tends to start to rotate more rapidly than the outer layers. This is the way, can we see this? The contrast is good on my screen, but maybe not so good here, so I apologize for that. These are the isotachs, the isorotation contours that helioseismologists have uncovered. So these contours tend to go up and down. In the bulk of the convective zone, you can see they're pretty well given by these straight lines. And then there are two boundary layers in this problem. There is the tachocline, where in a very narrow layer, the angular velocity changes by a significant amount. And there is the surface boundary layer, which you may not be able to see, but what is happening is that the isorotation contours are bent sharply equatorial at low latitudes, and then the bending becomes less and less and less as you approach the pole. So that's the ultimate state of the angular velocity distribution.
Steve, where did that picture come from?
That came
What
from-
goes into that?
Helioseismology.
Okay, that's observation.
That is pure observation. That's a fascinating topic, vast topic unto itself. But basically, by looking at the surface vibrations of the sun, they can determine what global modes are present, and by inverting doing the mathematical problem of that inversion, going from the global modes, they can deduce what body was giving rise to those global modes. It's a process that took several decades to understand, but that's now solid work. So what happens when what's interesting now is that the sun is in a state where there is shear present, like an accretion disk, but unlike an accretion disk, we have the dominant instability here is thermal convection. Now, what does convection do? Convection tends to mix entropy along the convective rolls, the up and down motions that are associated with these cells. So we can ask the question in the spherical star, why is there an entropy gradient in the steady state? In fact, I'm mixing entropy so efficiently. Well, the answer is obvious. I require some entropy gradient in order to maintain the convective turbulence in the first place. And this radial entropy gradient is sustained by essentially this radiative driving from below. The source of the sun's luminosity in the center is driving a large entropy gradient or temperature gradient, and then this is maintained, and the convective motions eliminate the entropy gradient as much as possible, but not completely. Now, what's interesting is that with rotation, the Coriolis forces induce a steady two-dimensional entropy profile. They depend upon not only r, but on the colatitude angle theta. So how can this be? If you have radiative driving from below, that can maintain a 1D radial profile. Convection is always trying to mix the entropy. Well, the answer is that's what convection does. The excess entropy, the true entropy minus this underlying entropy associated with the radial profile, is indeed well mixed. In other words, it is constant along the convective rolls, not the entropy itself, but this residual entropy. If the velocity here represents the convective velocities, then v dot grad of s, the full entropy, minus s of r, some function of r only, must be 0. The convective rolls live in and maintain constant excess entropy surfaces. They live in surfaces of constant S minus SR. That's what they do. But convective rolls, especially coherent, long-lived structures, which are the ones that are both in experiment and in simulations, are the ones that are actually the most important in transporting heat and probably angular momentum as well. These are sheared into, and they also live in, surfaces of constant omega. So here's two fluid elements in a non-shearing system going up and down, mixing the entropy. But over that period of time, if I have a shear present, then these embedded fluid elements are going to be drawn out into a surface in which omega is constant. Either they'll already be in the surface in which omega is constant, in which case they won't be affected by the shear, or if they are, they'll be drawn out into a surface of constant omega. So what does this mean? Now let me skip over the proof of that for the moment. If the same convective rolls live in surfaces of constant excess entropy, that should be, and they live in surfaces of constant omega, those must be the same surfaces. So this is an unusual condition. Excess entropy is a function of omega squared if the surfaces are the same. And this is a very important mathematical tool. We'll see why in just a moment. The question is, people have actually done a great deal of numerical simulations. Is this evident in the numerical work? And the answer is yes. In many cases, you can see this. So here is work taken from Mark Misch and the group at Colorado. The color code here shows you the angular velocity. Here is a rendering of the residual entropy, the entropy in excess of the radial background. And this is the total entropy on the right. You can see there's a strong resemblance between the angular velocity surfaces and the residual entropy surfaces, and not a very strong relationship between total entropy and the angular velocity. Why is all this important? The answer is, in stars, the vorticity flux is in some sense a more important quantity than the angular momentum flux, at least for understanding why the sun, which is what star we're studying, has the particular angular velocity distribution that it does. If I write out the vorticity equation now in its full glory, in particular the phi component of the vorticity equation is the one that I am interested in. Notice I have this baroclinic forcing on the right-hand side of grad rho cross grad p. There's my fundamental equation, and I impose the constraint that the turbulence has to satisfy. This is a little bit like, it's kind of a constraint which is analogous to saying that the temperature profile in a fully convective medium is adiabatic. In detail, that depends upon, or I should say nominally, that depends upon the details of the angular momentum transport. But in fact, heat transport. But in fact, the heat transport, if it's effective, is going to get to very, very nearly an adiabatic profile in the saturated state. And this constraint is kind of a rotational analog of this. The transport here in detail is complex, and this is still very much the approach that the community uses. They will approach this problem using a mean field theory for the turbulence. And what we may have here is a way to circumvent that, at least somewhat, by saying whatever the details of the angular momentum transport in a shearing convective fluid, the fact that this excess entropy and omega share surfaces in common allows one to make a great deal of mathematical progress on this problem. In fact, so much mathematical progress, you can solve this equation not just numerically, but you can actually solve it analytically. It's one of the few times in my own research when I've had a full partial differential equation that I could actually work out the solution to. And this is what happens when you fit the data. I wish I could show you. Can you see the, okay. So there's the data. And then this is the fit to the data. So I'm trying just to get the convective zone right here. The boundary layers has different physics. We have to work on those a little bit harder. But you can see the fit is very, very good. I think too good to just be a coincidence. I think we're on to something here. What about the tachocline and the outer layer? Alex, you're kind of a wise guy. What's special about 54.7 degrees? This is what Alec Toomer used to do. Oh, Tammy knows.
Well, I know that, but can I ask a question first?
No, I'm not going to be sidetracked. What's special about 54.7 degrees?
Cylindrical rotation matches the spherical rotation? Something like that?
I can't tell whether that's right or not.
One radian.
Hmm?
Is it one radian?
No? That's the zero of P2 cosine theta.
Of course, everybody should know that.
Everybody should know that cosine squared of 54.7 is 1/3. Just people aren't properly educated anymore.
So in the numerics that you showed, they were approximately, you had approximately constant entropy surfaces lining up with constant angular velocity surfaces.
Yes.
But those, is that also the case when they, because that angular velocity profile they got that was somewhat solar-like only came when they imposed a tachocline.
They didn't. They
And so when
imposed.
they-
They imposed special conditions at the boundary.
That's right. So when they don't do that and they get basically taken
That's been a
out
problem.
of that state, do the entropy surfaces still line up with the angular velocity?
That's a good question. I don't know the answer to that because I have never seen, the data, for that for those conditions. Whether when you have cylindrical contours like that, whether what the numerics show, I don't know. I can't tell you the answer to that offhand. But it is true that the data that I showed are a bit special in that they force the entropy at the boundaries, so that they have L equals 2 and L equals 4 components. And then they get something that looks a great deal like the sun. But I don't think, I don't see why that should in principle affect the way those surfaces line up. But I can't give you an answer for sure because I just don't know. So my point here in talking about this angle is that this is where the tachocline disappears. This is in fact a hole. It's the optic nerve in the tachocline, and it corresponds precisely to the zero of the second Legendre polynomial. As far as I know, I got to be the first one to notice this. It just is staring at you. I suppose people talked about quadrupolar structure before.
This is from experiment.
This is
from the
no.
observations.
That's observations.
How precisely is this determined?
Well, pretty precise. I think it's a clue. It means, in fact, there's some kind of quadrupole structure going on. There's forcing going on there, which I think is proportional to P2. So, why is this important? Let's go back and look at the vorticity equation again, which is has this unusual form for its transport. There are two pieces. There is a piece that corresponds, omega here is the vector component, and here V is the vector component. This piece is associated with vortex stretching. Vorticity tends to be frozen into the fluid. In fact, it would be frozen without this term over here. And so this term corresponds to the stretching of vortices as the fluid is subject to differential rotation. And this term corresponds actually to my opening slide. This is what Donald Lindenbell would call Lorry transport. Actual transport of V dot omega phi, motion where the vorticity is being advected. The vortex stretching dominates in the bulk of the convective zone, but vortex advection is important in the two boundary layers. And I think that's what distinguishes the two boundary layers. They tend to have very high levels of turbulence. One is due to large convective motions. The other is due probably to large turbulence associated with shear. So here is the gong data. This is the helioseismology data. And there is just a very simple, this wasn't even chosen to fit the data. This was simply an analytic solution that we could work with based on P2 cosine theta forcing and our previous solution for the bulk of the convective zone. Here's a model where we've actually overlaid the two. That looks more striking. And this is a global model. This is our equation where I have vortex stretching here, which is the bulk of the convective zone, P2 forcing, and sine squared theta forcing. And that looks really quite a great deal like the sun. Yeah?
But there are some free parameters.
There are some free parameters. There is the surface at which we fit, and the function f of omega is free. So how did we do that? We chose that by going to a particular isorotation contour and then fit the slope at that one isorotation contour and then enjoying the rest of it on its own. There are some free parameters, yeah.
That's the gradient of equal gradient. Forcing.
The forcing actually in the equation, it's not the gradient of rho across the gradient of p in this problem is not, although physically it's a forcing term, it depends upon the rotation omega. The forcing actually is those terms which I labeled as vortex advection, because they don't involve derivatives of omega at all. They appear as external in a mathematical sense, forcing terms. Matt, yeah. We'll come to that. Let me explain where that comes from. That's just my next bit, and then I'm running out of time. So, Matt, can I get you at the end?
Yeah, that's fine.
Okay. Now, meridional flow, this sort of motion that you see here, as a secondary process, has been observed and has been thought to have been present in the solar, has been observed in the solar convective zone, and has been a part of our understanding of the processes that are present for some time. This is a little bit like the analog of this Ekman circulation in a teacup. There are these secondary meridional flows that are present, which the theory has not yet taken into account. And this is where the forcing is going to come. Less well known is the fact that this meridional circulation, when you actually put in the velocities associated with it into the vorticity equation here, produces two things, and two things exactly. One, a term which is proportional to sine squared theta. Two, a term which is proportional to P2 cosine theta, and nothing else. And nothing else. So I think that is the origin of the forcing there. Somehow it is connected to the meridional circulation. And I'm running out of time, so I'm just going to get to my last few slides, and then I'll take questions. So I'm going to leave you with that. What the precise physical interpretation of these secondary global flows really is, and how they contribute to this vorticity flux divergence, which is the sort of central mathematical object of the theory, is still an ongoing area of inquiry. But basically, it seems like a fairly simple dynamical theory is compatible with the observations. There are pieces to be sorted out, but I think we're on to something. Two-sentence summary, and then I will stop. Accretion disks are MHD turbulent. They are the primary instability, I think, is the magnetorotational instability driven by differential rotation. It tends to push angular momentum out, and the mass drifts inward. The secondary drift velocity corresponds to the basic accretion process itself. The cascade of energy from the differential rotation to the fluctuation to thermal dissipation is all done locally.
Is this a tweet?
Hmm?
Is this a tweet? It's 144 simple or whatever is the.
I'm sorry, I'm getting fogged out here.
We'll explain later.
All right,
Internet.
don't do that to me. No, sorry. I'm too old. Convective stars, driven by the primary instability, is an entropy gradient instability. The vorticity flux is the crucial object here. Rotational surfaces are related to residual entropy surfaces. Advected vorticity is important in the outer layers and the tachycline, but apparently not so much in the bulk of the convective zone. The secondary flow is not just an simple inward drift as it is in an accretion disk, but it is circulatory, probably driven by the acquisition and loss of vorticity and the ensuing equatorial and polar drift. What I mean by that is that we have an example in geophysical fluid dynamics where disturbances that tend to lose vorticity because of vorticity, overall vorticity conservation, tend to drift poleward. Those elements that acquire vorticity tend to move toward the equator. Okay, and I think at that point I should stop. I really am out of time. Thanks very much.
should have a few questions before lunch, Alex.
I think this is a question I must ask as a homage to all these decades of astrophysics. Have you, in the second part of your talk, have you considered the importance of the magnetic field?
That's an excellent question. I certainly have, and I worry about it. When I originally found the mathematical solution to this, I was initially convinced that the explanation was magnetic. The reason is that if you look at the MRI, I thought this was going to be another triumph for the MRI. If you look at it in the context of a star, where you have entropy stratification in addition to angular momentum stratification, you find that the analog of what is known as the Hoylen criteria, which take into account both in a hydrodynamic problem, entropy, angular momentum stratification, with a magnetic field, it turns out that certain important modes are marginally stable, growth rate of 0, when entropy surfaces and angular velocity surfaces coincide. So I said, end of story. That has to be that. And I said, such a subtle thing because it's because of these weak magnetic fields. So for a long time, in fact, the first talk that I gave here on this in November 2008, I was pushing this magnetic explanation. So I think, in fact, that is ultimately not the cause because people see this process in purely hydrodynamical simulations, number one. And number two, the details of if that were the correct explanation, what that would mean if it wasn't just the residual entropy, but the total entropy that followed these surfaces, that would put the sun in a very peculiar position. I would have entropy inversions, and part of the zone would be convectively unstable, part of it would be driven by rotation, and it got to be essentially untenable. So that explanation wasn't the right one. Why magnetic fields don't work? I think, in fact, this really is a case where the magnetic field is, except in localized regions in the convective zone, the magnetic field really is too weak. The Alfvén velocities here are centimeters per second versus rotation velocities of kilometers per second and meters per second for the convective motion, tens of meters per second. So I think it's basically a hydrodynamical process owing to the weakness of the magnetic field. It's not a problem which seems to be exquisitely subtle to the presence of the magnetic field.
In the solar wind, we're seeing that when we go from the weakly collisional regime to the collisionless regime, we excite a lot of short-scale instabilities that are associated with pressure anisotropies. I wonder if you could say anything about the collisional to the collisionless regimes and accretion disk. So we think
There has been work on that. I think I'm going to defer that question to Greg Hammett, who has actually been involved directly with the simulations. So I won't say any more.
So there are these microinstabilities when the pressure becomes anisotropic, and they seem to be important in heating. It's a mechanism for heating particles in the plasma. It does not drastically change the MRI when you consider the MRI in a low collisionality plasma. The MRI is still there. Its growth rate changes by factors of 2, but not.
So it's a small change in growth rate.
It's a small change, but it does provide an additional heating mechanism that heats electrons, and that can be important because of the ADAF scenario that had assumed the electrons stayed cold somehow. But this goes back to our discussion yesterday of whether or not these microinstabilities really do break mu invariance and scatter the particles, or whether they're reversible. If they're reversible, then they do not heat these particles.
I was fascinated at your comments about the MRI and how long it took to discover this. I mean, I'm tempted to think that this must be associated with the fact that astrophysicists refer to things like accretion disks by the use of the word gas, and that if they had used instead the expression plasma, it might not have taken so long. And so my question is there any likelihood that astrophysicists might begin to use the word plasma to describe that?
It was it.
Well, if I have anything to do with it, the answer is yes.
We drank to that
But-
yesterday in the banquet.
But oddly enough, the history is interesting because this work was begun by Chandrasekhar, who was certainly no stranger to plasma astrophysics. And the basic instability is already there and present in his 1960 book on hydrodynamic and hydromagnetic instability. Because his approach, as you know, is so formal that he was enmeshed in variational principles and global eigenvalues and so on, and just wasn't picturing a local instability process. But he was a plasma physicist, so he doesn't even have that excuse. The point is well taken.
Before that, there was Velikov paper, which was simpler, much simpler.
Well, there was a Velikov paper 59. Chandra actually began even before that, in the late 50s. He tried to do the whole problem at once, which is why he put in viscosity, he put in resistivity, and then Velikov actually was the best paper. Velikov, who is still, by the way, very much with us, basically understood, the physical process that was going on. But he was not an astrophysicist, and I don't know how aware he was of sort of the accretion disk problem for all those decades.
What about Chandrasekhar? He was an astrophysicist. He was around.
I have to be careful what I say
Yeah,
about
yeah,
Chandrasekhar.
and they all watched this whole debate about hydrodynamic instability and accretion disk for 2 or 3 decades, and nobody said no.
And Chandra didn't say it.
Yeah, Chandra.
Yeah, that's what I find the most remarkable.
I was wondering, there's going to be new data of astroseismology, and is that detailed enough to provide more tests of your theory?
So the question refers to the fact that there are several satellites now who are looking for very small levels of variability in stars as part of planet search programs. There's satellite Coro, there's Kepler. So depending upon sort of, originally they were meant to be exactly this. They were trying to look for global modes in stars beyond the sun. But when planetary extrasolar planets were discovered, that became a very hot topic. And so the emphasis is on looking for transits of planets across the faces of these stars. But in principle, there will be astroseismology, the idea being that by looking at surface variations or magnitude variations of the star, you can say something about, once again, the global modes that are present and then do the inversion problem. In practice, I think that we will not have anywhere near the coverage that you would need to do a proper inversion. The number of modes that people know about and sort of have identified in the sun is thousands and thousands and thousands. And so we can get very detailed, we can do the inverse problem in a great deal, to a very high level of resolution. And I think we won't have that level of resolution. We might be able to say something about whether it's differentially rotating or not, but in terms of the precise profile of omega, I think not for the foreseeable future.
But in white dwarf pulsations, a lot of the action is thought to happen right at the surface, where maybe the lack of resolution and number of modes might be compensated by the fact that everything's happening close, and then there might be some remnant of.
Yeah, I know that people have been able to do. I think that's a special case.
Right.
I think the convective zones that we're looking at here are several tenths of the sun's radius.
Yeah. Now we're down to. Yeah.
Right.
I think
Thanks.
let's thank all our speakers for joining.